So this week our focus is on the experimental determination of the structure of organic molecules, and this is really important because we can never be sure once we've carried out a synthesis reaction what our product actually is until we have tested it. So the whole point of experimental determination of structure is to confirm and verify what molecule we have synthesized. And there are various different methods that we can use in combination to do that. So experimental microanalysis gives us an idea of the empirical formula of a compound, which is basically just a ratio of the atoms within a molecule. Mass spectrometry, which tells us the molecular mass of an organic molecule, but then also what functional groups may be present. Infrared spectroscopy, which gives us another idea of functional groups based on how much energy a bond can absorb, and then proton nuclear magnetic resonance, which gives us an idea of the environments of hydrogen atoms within a molecule. So the first method we're going to look at is elemental microanalysis, which involves a sample of your organic molecule, a very small sample, approximately 2 milligrams worth, and it goes into this machine here, and it undergoes a combustion reaction, and it produces oxides, so gases of the elements that are present in your original sample, and they get passed through a gas chromatography column, which if we look on this slide is this bit here, this coil. So that's quite a long column which separates the different gases that are produced, usually based on their molecular mass, and then they are analysed and you're given an idea of the percentage or the mass of each gas that is produced. So the reason this is so useful is we can analyse the products of that combustion reaction, and from that we can determine an empirical formula. And we're going to have a look at how to determine empirical formulas, but before we do that, let's have a think about what an empirical formula actually is. It is basically just a ratio of the different types of atoms present in a compound. So for example, if you have this compound here, C3H6, which is propene, you would just simplify that and the empirical formula would be CH2. So C6H12O6, which is glucose, would be CH2O. Benzene would just simplify to CH. And this compound at the bottom here, we would just simplify to C3H7N2O. So all you're doing is simplifying using whole numbers the molecular formula. So there are a couple of different ways in which you might be given the results after your molecule has been passed through the combustion chamber. You may be given your results as a percentage product by mass. So if we have a look at the next slide, here is an example of a question. Analysis of an alcohol shows it to contain 37.5% carbon and 12.5% hydrogen. You would be asked to work out its empirical formula. So here is just a step-by-step guide to how you would do that. So the first thing you would need to do is to deduce the percentage by mass of any unstated values. So we know we have 37.5% carbon, 12.5% hydrogen, so we must have 50% oxygen. So we've done this. The next step is to calculate the number of moles using the relative atomic mass values. So we can just take our value from this column and divide it by the relative atomic mass. So it would be number of moles equals 37.5 divided by 12 for carbon, and that would give us an answer of 3.125. And you're going to complete that for hydrogen and oxygen. So that's step 2 completed. The next step is to deduce the mole ratio, and you do that by looking for the smallest of your calculated values for step 2 and dividing the rest by it. So our smallest of our calculated values, well, it's both carbon and oxygen, so we would assign them a mole ratio of 1. And to work this out, we would do 12.5 divided by 3.125, and that would give us an answer of 4. So we've done step 3. All we have to do next is determine the empirical formula. I'll just do that over the side. So the empirical formula is just going to be CH4O. So the second way of determining an empirical formula is through analysis of the combustion product masses of the gases that are produced. So here's an example of a question. An antibiotic contains carbon, hydrogen, nitrogen, sulfur, and oxygen. Combustion of 0.3442 grams, so that is what goes into the chamber. Just to make that clear. Of the compound, and excess oxygen yielded 0.528 grams of carbon dioxide, and so on and so on. You can read that. What is the empirical formula of the antibiotic? So again, let's just follow a step-by-step process here. So for step 1, you need to calculate the mass of each element within the original sample, and to do that, you multiply by the relative atomic mass. Now it's the relative atomic mass for each element as it appears in the formula of the gas. I'll highlight that as we go through it. You then just divide it by the mass of 1 mole. So let's have a look at that. Carbon. The mass of carbon dioxide produced is 0.528. So 0.528. We're going to multiply that by the relative atomic mass of carbon, which is 12, and then divide that by the gram formula mass even of carbon dioxide. So that is 44. Plugging that into the calculator, you get 0.144 grams of carbon in your original mass. We'll do that for hydrogen as well. So you have 0.144 grams of water produced. We're then going to multiply that not 1 but by 2, because there are 2 hydrogens obviously in the formula of water, and that's the only one this applies to. And then divide by 18, as that's the gram formula mass of water, and your answer is 0.016 grams. And I'm just going to fill that in for the other 3 now. remembering it's 28 here because it's N2. Now for oxygen just makes up the difference here. So this is what goes into the chamber, and you've worked out what the mass of all the rest is. So you're just taking this number, which is 0.3442, and you're going to subtract the total of these 4 calculated values. I obviously don't have a lot of space, so I'm just going to write in total, and you'll see that the answer is 0.064 grams of oxygen. So if we go back to our step-by-step guide, we have done step 1. That is really the big difference here. The rest of the steps more or less follow the same as the previous method. So you're going to calculate the number of moles using relative atomic mass values. So for this top one, we're just going to divide by 12, and that gives you 0.012. Divide by 1. So it's this value here we're dividing by. 0.016. We're going to divide by 32.1. And that gives us 0.002. For N, we take our 0.056, divide by 14 to give us 0.004. And then for oxygen, dividing by 16, which gives us 0.004 as well. So we've done this. We're then going to deduce the mole ratio. And remember, we have to look for our smallest number of moles values, which is going to be sulfur. So we assign that 1. We are then going to divide each of the other numbers by 0.002, which gives us 6, 8, 2, and 2. So we've done this. And then our last step, just write the empirical formula, which is going to be C6, H8, S, N2, O2. So this is quite a useful method. It gives you an idea of the ratio of atoms within a molecule, but it doesn't actually tell you much else. The next few methods we're going to look at will give you more information on the actual structure, on the functional groups present, but using all these in combination with each other will tell us a lot about a molecule. So the next method we're going to look at is mass spectrometry, which, as you can probably tell, will give you an accurate gram formula mass of the compound that you are analysing. So here are just a couple of little mass spectra. We have hexane and we have 2,3-dimethylbutane. Now, both of these compounds have the same molecular formula, which is C6H14, but obviously they're structurally different. They're isomers. If you were to work out the gram formula mass just using REMs, you would work out that it would be 86 for both of them. And as you can see, here is a structure, 86. So this peak on the right hand side of both of these spectra will tell you the molecular mass of the compound that you put in. But look at the rest of the spectra. It is all, some of it's similar, but some of it is a wee bit different, and this will just helps to give you an idea of the structure. Right, so a little bit about how a mass spectrometer works. Here you have your little inlet, and that is where your sample is put. Now, it's a very small amount of the compound you want a spectra for. It would be milligrams worth, and it goes in here and it is vaporized. The vapours rise up into the reservoir and then down through this first part of the column here. Now, at this point, your sample is bombarded with a load of high energy electrons. And what that does is it removes an electron from your sample and forms a positive ion of it. So if you were putting in there, say, a sample of methane, what would be formed is a positive methane ion, for example. It then travels down here. As it travels, as it comes out here and goes through the ion beam, it actually breaks apart your molecule. We say it fragments it. And those fragments that are formed are analysed. They go through a magnetic field, through a detector, which then counts the number of each ion that's present, so the size of it and how abundant it is in your sample, and then you get your nice spectra produced at the end. I will let you read through all this. There's just an idea of fragmentation. So for example, you might see a fragment with a molecular mass of 15, and when you see that, it is likely to be a methyl group, which means there is a methyl group in your organic compound somewhere. Another wee bit about just exactly how it works. Wee bit about the ion beam as it goes through the magnetic field. You can just have a wee read at all that, and we'll look at some spectra. So I want to start by looking at the spectra of a known compound, and we're going to look at benzoic acid. I want to do this just to highlight to you the different features and how detailed a mass spectra can actually be. So here we have benzoic acid. We know that it has the formula C7H6O2. We can work out the gram formula mass, which will be 122 grams. And that's confirmed by this value here. So the value furthest to the right is known as the base peak. And that is just the mass of the molecular ion. So in this case, the molecular ion is C7H6O2 plus. Okay. Now, if you look, the height of the base peak is quite high. It's shown a high relative abundance, and that's quite significant because it tells you that it doesn't fragment very easily. So if it doesn't fragment easily, it means there's not lots of wee groups that are easy to remove. Obviously, we've got this benzene ring. It's pretty hard to fragment a benzene ring. We've got an OH group. We've got a carbonyl group. Together we have a carboxyl group. But other than that, there's not very much there that will fragment. Right, so let's analyse the rest of it. So here's our base peak, and we refer each of our peaks, as we see, back to our base peak. I'm not going to look at them all, but I'm going to look at a couple, and you can have a look at the rest on your own and see what else you can interpret. So we have 122 as our molecular ion mass. We then have the tallest peak at 105. So the difference there is 17. So we're looking for a fragment in our molecule which has a mass of 17. The OH group has a mass of 17, so that peak would indicate the presence of a hydroxyl group. 94 to 122 is a mass of 28. Our carbonyl group has a mass of 28, so that's probably indicating this. 57 down here would indicate your carboxyl group. You can have a go looking at the other values and seeing what you can, if you can work out what other fragments might be produced. Now, this is really, really useful because if this is an unknown substance, that will give us an idea of what functional groups may be present. So we know if we see a fragment with a difference of 17, that's probably a hydroxyl group. It's really useful. So here is just a table of some common ions and their masses that you might see in a mass spectra. So a mass difference of 15 tends to indicate a methyl. 17, as we've looked at, a hydroxyl ion, and just a few more for you to refer to. But we're going to look at another spectra. This is a spectra for hexane. So you get C6H14. We know it should have a gram formula mass of 86 grams, and indeed that is the value of our base peak. But have a look at the difference in the height here. It's much smaller. There's a much lower abundance. Which indicates that this molecule will fragment much more easily. So let's have a look then at the structure of hexane. We'll just draw it out. So unlike our last example of benzoic acid, which had our benzene ring and then just a couple of E groups, this is just a straight chain of lots of methyl and then CH2 groups. So we've got a methyl group, we might have an ethyl group, a propyl group, and so on and so on. So let's look at this first one. I'll just draw a wee arrow to that. There's a difference of 15. So we reckon that will indicate a methyl group. If we look at this next peak, we've got a difference of 26, which is our ethyl group, and so on and so on. You can even see a wee 15 here, indicating a methyl as well. Well, it wouldn't indicate a methyl, it would indicate a pentyl group, wouldn't it? Because that's our mass difference. So have a look at the rest of these values, see what you can work out. A graph like this would strongly indicate the presence of a pentane or alkyl group. So our next method is infrared spectroscopy. Now we've spoken about infrared radiation before. It has a lower frequency and a longer wavelength than the visible light. Here it is here. And I want you to think about this before we go any further. You have a fire on. Why does or how does that fire make you feel warm? When a fire's burning, it is giving off infrared radiation. And when that hits your skin, molecules in your skin absorb that radiation and it makes you feel warmer. Different groups within those molecules will absorb that radiation at different wavelengths. This is all really quite similar to when we were talking about atomic spectroscopy and all that stuff way back at the start of the inorganic unit. So different molecules contain different functional groups and different types of bonds. And when those bonds absorb that radiation, they will move, and they will move in all different sorts of ways. You might have symmetrical movements where the bonds, so this would be coming in here and then going out that way. You might have like an asymmetrical motion where they're happening differently. Twisting, where your whole molecule is twisting backwards and forwards. It might rock. It might do like a scissoring action. There's a whole load of different ways that bonds within a molecule can move. Remembering a bit more restricted with double bonds, but certainly single bonds can move in all sorts of different ways. Now, a couple of things to point out here. I'll let you read this. But different wavelengths of infrared radiation are absorbed depending on different types of atoms that make up the bond, and then the strength of the bond. So larger atoms, it's maybe good to take a wee note. Larger atoms tend to vibrate more slowly than smaller atoms. Okay, so this little differentiation helps us to determine what bonds are present. To obtain the spectrum, it's passed infrared radiation is passed through a sample, and then a detector measures the intensity of radiation that is transmitted at different wavelengths. When you see an IR spectrum, and when you look at the page in your data booklet, it's page 14 in your data booklet, all the IR correlation table, you'll see that you're actually given the values in wave numbers, and it's given in wave numbers because it's just the reciprocal wavelength. We've looked at this before, but it just gives you a much nicer looking graph. It's much easier to read when we give the data in wave numbers. So let's have a wee look at interpreting infrared spectra. We have a kind of baseline running along the top, and our y-axis is just percentage transmission. So when that line is up towards 100, it means that there's a high percentage of light being transmitted, so very little is actually being absorbed by the molecule. You'll then see really sharp peaks, and that shows you where a particular bond has absorbed a larger amount of energy, so our transmission has dipped. It will then peak straight back up and along till we hit another peak. And if you look along here, we have wave number. Have a wee look before we go on to the next slide. Have a look at these peaks and the values at which they fall, and see if you can work out what peaks they might represent. So this is just the same graph as we had on the previous slide, and this is typically representative of an alkane. So let's just draw what we might have. Every alkane will have a CH2 group, well, not everyone, but almost everyone, a CH3 group. This R just representing the rest of the carbon chain. So use page 14 of your data booklet and refer to that as we're working through the next few slides. We have a peak here. It's fallen just after 2800, and that is representative of a C to H stretch. And if you look at your correlation table, that will fall somewhere between 2962 and 2853. So that peak there is fairly standard for a C to H stretch. So that's the bond stretching out, stretching back as it absorbs that infrared radiation. This peak here, a bit lower down, is representative of a C to H bend, and will fall somewhere in the range of 1485 to 1340. So that spectra there is just for a standard alkane, and is pretty much what you would see for any alkane that went through an IR spectrum. So just important to note that at advanced higher you will only be looking at peaks that fall with a wave number of 1400 to 4000. These tend to show specific groups or specific bonds. Anything below 1400 is known as the fingerprint region. It's much more complex, much more crowded, and that's where vibrations can be used to help identify specific compounds. But remembering to always be referring to page 14 of your data booklet, which shows your correlation table, and you would never be asked anything out with anything on that table. So let's have a look at interpreting an IR spectra for ethanol. So remembering everything over here, below 1400 is the fingerprint region, and we're not really going to look at anything in that region. 1400, a wave number of 1400 and upwards only. So here we have representative of a CH bend. That's just the same as like our alkyl groups in the previous one. Here is the same for our CH stretch. And then this is this is just the same as our last one, but this one here is what I really want to draw your attention to. This is representative of an OH stretch, so a hydroxyl group. And if you notice the difference of this one compared to the other ones where we have really sharp peaks, we have a much broader and wider peak here. That's because of the differences in how much radiation the bonds will absorb, depending on whether there's hydrogen bonding present or not. That's why that's much broader and is really indicative of an OH group being present. So just keep an eye out for that. So the final method of spectroscopy we're going to look at is proton nuclear magnetic resonance, so NMR for short. You might see that in front of it just to represent a proton. What we should be starting to see so far is that one method on its own will tell you some things about a compound, but using all these different methods together allows us to build a picture of an organic molecule and helps us to identify it much more accurately. NMR takes that even further and gives us even more detail about the environments in which hydrogen atoms can be found. There are lots of different types of NMR. You can have carbon NMR and phosphorus NMR, but we are going to concentrate solely on proton NMR. So a wee bit now about how proton NMR works. Proton NMR is used to identify hydrogen atoms. It can give you information about how many hydrogen atoms are in a specific environment, and also some information about that environment as well. So hydrogen nuclei we know are basically just protons, and similar to electrons, they have a spin. They can spin in one of two ways, as shown by this diagram on the right here. If you have a look at the arrow going through, that just represents a magnetic field. And when there's no magnetic field applied, those little protons will just spin about in all sorts of directions. But when we apply a magnetic field, those protons will align. We'll have some that align with the field. So if the field is this direction, all these ones here with the arrow pointing up the way show they are resting, are aligning with the field. The ones with the arrows pointing down the way are showing that they are resting against the field and they're sitting at a higher energy. Absorption of radiation, once the magnetic field has been applied, will cause the protons to flip, as shown in this second diagram. So they flip from the lower energy to the higher energy, so they flip from going aligning with the field to going against the field. And then as they fall back, radiation is emitted and plotted on a spectrum. So here is what an NMR machine looks like. It is a huge machine. It's basically a huge magnet. When you're in one of these rooms with an NMR machine, you have to make sure you're not wearing anything magnetic. You just leave it outside the room. You have to be really careful when you're near here. And inside, it looks a wee bit like this. So there's a tiny little slot that your sample goes in, with magnets on either side, which aligns the protons. Then you have your radio frequency, which is absorbed, and then as it falls back, the absorption is detected and then transmitted into a spectrum. A simple proton NMR at low resolution doesn't take very long to do. More detailed and more complex NMR can take hours to run just one sample. And this is what your sample looks like for the size of the machine, which is huge. This is all that actually goes into it. It's just a long kind of glass tube, and the sample that you're analysing is here at the bottom, and it's dissolved in a solvent that does not contain any protons, obviously, because if it did, this would interfere with your spectrum. So it's dissolved in something like tetrachloromethane, or in solvents where 1H, so your normal proton, is replaced by deuterium atoms. So in order to obtain an NMR spectrum, you almost need to calibrate your machine, and we do that using a reference compound known as tetramethylsilane, or TMS for short. And we use that because it gives a signal that lies well below any compound that's been analysed. So when we're taking an NMR, we're measuring a chemical shift, and it's measured in parts per million, and TMS gives a chemical shift value of 0. If you look at this next one, here's TMS here with a value of 0, and everything else is measured against that. Chemical shift values for all the protons and different chemical environments are given on page 16 of the data booklet. So if you have that open as we work through the next few slides. So there are two types of ways that you can run an NMR. We can have a low resolution NMR and a high resolution NMR. And we're going to concentrate on low resolution just now. And here is an example of an NMR spectrum. So NMR is so useful because it gives us an idea of different environments in which hydrogen atoms can be found, but also how many there are. So if you have a look here, we have hydroxyl, which obviously contains one carbon atom, and there's quite a short kind of peak here. CH2, which contains 2, which has a longer peak, and then CH3, which also obviously contains 3, which is much larger. So the more hydrogen atoms that are present in a specific peak or a specific region, the taller the peak will be, and you can simply measure that with a ruler. It can be integrated using computer software, and usually that's what, once you run an NMR and you get it back, that's what you would see. But we have different environments with different ppms, but also the area underneath the peak and the size of that giving us an indication of how many hydrogens are actually present in that environment. So let's look at this NMR in a bit more detail. This is just an NMR of ethanol, so I'll just quickly draw that out. We have CH2 and CH3. So we've got 3 different peaks. and we have 1, 2, 3 different environments where we might find hydrogen atoms. We have 1 as part of a hydroxyl group, 1 as part of a CH2 group that is attached to a hydroxyl group, and then 1 as a CH3 group which is attached to a CH2, which we can, it's more like an alkyl group here than, because it's not directly attached to the hydroxyl group. So taking this one at a time, there's 1 hydrogen atom there, and if you look at page 16, the hydroxyl hydrogen falls within a region of 5.0 to 1. We work kind of backwards when we're looking at this. The 2 hydrogens of our CH2, 3.9 to 3.5, that'd be different to the group found if it was just another CH3 here. It's got a different chemical shift because it's a different environment when it's attached to a hydroxyl rather than another methyl group. And then we have our CH3 group, which when attached to a CH2 group, we have a shift of 1.5 to 1.9, and there's 3 hydrogens there. So this is treated as an alkyl group. So take a wee bit of time, look over that, refer to the table on page 16 of your data booklet and see where each of these falls and why it falls there. As I kind of mentioned before, you can just simply use a ruler to measure the area kind of underneath the peak, but also quite often you'll see that there's an integrated kind of ratio there to help you with that. So we go from 1 to 2 to 3. So we're going to talk through a couple of examples now and have a go at interpreting the low resolution NMR. So we've got an ester here, we've got methyl ethanoate. So I'm going to start by just drawing this structure, which will obviously always help. So here we have methyl ethanoate. So we've got hydrogen atoms in 2 different regions. We've got hydrogen atoms attached to a carbon next to an oxygen as part of the ester link. And here we have hydrogens attached to a carbon that is part of a carbonyl group. So here's our TMS, we just ignored that, that's our reference. And we've got 2 different environments. So we just need to work out which one is which, and you just do that using the data on page 16 of your data booklet. So if we start, the best way to look, if you look at these numbers run along the top of that table, so just look where this is, go to the top of the table and then just run down and see if it matches a structure that you're going to find in here. And if you do that, you'll see we have a peak here with a range of 3.9 to 3.5 from the data booklet, and that is representative of this group here, which is really badly drawn, but never mind. And that's just the rest of the molecule. So we've got this peak representing these hydrogens, which is this bit here, 3.9 to 3.5. Notice as well that our 2 peaks are the same height, and they each indicate, obviously we can see from our structure, 3 hydrogen atoms in each. This peak here probably is our 2.7 to 2.0 peak, representing CH3 next to a carbonyl group. So that is this one here, 2.7 to 2.0. Maybe just take a wee note that the size of the peaks shows the same number H's in each environment. So using the table, have a good look at that. Make sure you know why each peak is there, why that's the range of values and how that all matches up. So let's look at a slightly different spectra. This is for 1,4-dimethylbenzene. So let's draw the structure. We started with our benzene ring. If we take this as carbon number 1, we've got a methyl group there. And 1, 2, 3, 4, a methyl group here. Now remember, and it's quite, sometimes we forget, that in each of these carbons it doesn't have a substituent group. There is actually a hydrogen attached there, and this is what we're trying to detect. Okay, so again, page 16 of your data booklet, look along the top and look at where these shifts fall. Here we have one round about 7, and if we look down our table, something that falls within a range of 8.0 to 6.6 will represent an aromatic hydrogen, so a hydrogen directly attached to a benzene ring, and we obviously have 4 of them. And then if we look down here, we've got a peak there just kind of between 2 and 2.5, which if we study our table, something falling within 3.0 to 2.3 represents the hydrogens in a methyl group that are attached to an aromatic. Notice how that's different from a methyl, the hydrogens in a methyl that are attached to the rest of an alkyl chain. It's got a slightly different shift. So spend a bit of time looking over that as well. So far we've looked at low resolution NMR, and this spectra on the left here is an example of low resolution NMR when we just have our single peaks, but our peaks might, they might be a bit messy, but they're, they give us the correct chemical shift, but they don't tell us too much else. A high resolution NMR gives us a lot more detail, where we have we might have singlets, we might have doublets, we might have this peak split into triplets or quartets. And this gives you information about the environment the hydrogens are in, but also how many hydrogens are attached to the adjacent carbon. So let's continue to look at ethanol. If you have a look, I'll draw the ethanol molecule out again. So the chemical shifts for the low resolution and the high resolution are exactly the same. They don't change. The only thing that changes is how the peaks are split. And you need to remember the n plus 1 rule. I tend to think of it a bit better as n minus 1, but you can have a wee think and work this out in a way that suits you. If we deal with our triplet first of all, that triplet indicates that if we do apply n minus 1, that there are 2 hydrogen atoms on the adjacent carbon. Therefore, this, whatever group this is, must be next to the CH3. CH2, I should say. I just wrote that out. CH2. So we still work out what group this is based on the height of the peak, based on its chemical shift, but the splitting tells us whereabouts in this molecule that it is next to. So we know from looking at our low resolution that this peak represents our CH3, but this high resolution NMR tells us that that CH3 must be bonded to the CH2. If we apply that same principle to our quartet, n minus 1 equals 3, which means the carbon that that's attached to must be a CH3. And we know that that's correct. We know that from the structure. So I'm going to talk through this high resolution NMR, and we're going to see if we can deduce what this is an NMR of, given the formula which may have been obtained through elemental microanalysis for something with a formula of C4H8O2. Now, this is not something that you will necessarily be asked to work out in this much detail, but probably worth going over just to highlight some things to you. So we'll just take it quite slowly. Let's look at our peaks first of all. We have a quartet, we have a singlet, and we have a triplet. They all have their own individual shifts. This too tells me that there's two hydrogens at this shift. So probably that is a CH2. This 3 tells me that there's 3 hydrogen atoms there, probably a CH3. And this also tells me that there's 3 hydrogens, probably another CH3, but just in a different environment to the one shown here. So let's just take it one at a time. I'm going to start with this quartet, and I'm going to write down quite a wee bit of information about that. So I've got 2 hydrogens here. I've deduced it as probably a CH2. So if I go to my correlation table on page 16, I'll see that there's a shift at about 4.2 to 2.2 that represents this. Now, this R just means the rest of an alkyl chain, and this X means like a different functional group. It could be anything. It could be a hydroxyl, it could be an ester link, it could be a carbonyl. Okay, it just represents something else. It's a quartet, so if I use my N minus 1, it gives me 3. So therefore, it means that this is a CH2 that sits next to a CH3. Okay? And if I look over here, in fact, no, I'm not going to look at that first. I'm going to draw this up. So if this is a CH2 next to a CH3, I'm probably going to have something that looks like this. Okay, I don't know what comes next. I know it's not going to be another CH2 because this tells me that, but it's going to be something. I just need to figure out what it is. So let's have a look here. I've got a singlet. The area tells me that it's probably a CH3, but it is not directly attached to any carbon which has hydrogens attached to it. So if I look down my table, a shift that falls in that region is 2.7 to 2.0, and that is representative of a CH3 which is next to a CO. So that's quite interesting. The fact that it is a singlet tells me that it is probably a CH3 next to no hydrogens. So I know that looks like an OH, but it's 0 hydrogens. So that's quite interesting. So I've probably got a CH3 over here. Now it's telling me that it's next to a carbonyl group, but that could be a ketone, it could be an ester. I don't quite know what it is yet. Let's deal with our final peak here. I know that it is probably a CH3, and if I look down, 1.5 to 1.9 is probably an RCH3, and N minus 1 tells me that it is a CH3 next to CH2. So this is for my CH2 and this is for this CH3. This here is for this CH3 next to this carbonyl. Now let's look at our, this NMR has told us as much as it can, but there's still something missing, because if we look at our formula, we've got C4, 1, 2, 3, 4, 8 hydrogens, 1, 2, 3, 4, 5, 6, 7, 8, and 2 oxygens. So the only thing that makes sense here is that there's another oxygen in there. So this is actually the NMR for this ester, which is ethyl ethanoate. That all adds up. If you look at this shift marks, kind of shows that that's probably the case. The shift for this CH2 shows that that's the case as well if we look at this bit of data here. So have a look over that, try and match all that up and get your head around that. So there are many uses for magnetic resonance, and the kind of most common is in the use of MRI scanners that obviously you get in hospital, and they work in a very similar way to proton NMR works, in that our bodies largely consist of water, and the protons within the water, because they're in different environments and different types of tissue, we'll see different absorptions when radiation is passed through it, so that it can show up, it can build images and 3D images of the body. If you go to this website, there is a load of videos, some Royal Society of Chemistry videos for you to have a look at. I would strongly advise watching them. I would also go to Scholar and work through all the questions in Scholar. They're really good, really detailed, and will help you just more practice at interpreting some spectra. Any PPQ questions, any past paper questions throughout the notes, we will go through as a class when I see you. Enjoy!